We last talked about the momentum of a photon and how you can calculate the momentum of a photon by looking at Planck's constant and dividing Planck's constant by the wavelength of that photon. So if you know the photon's wavelength, you can find its momentum. This momentum wavelength relationship actually was discovered to exist for all matter, not just for photons. Early last century, de Broglie discovered that if you rearrange this equation, simply algebraically rearrange it, you can solve for the wavelength. So the wavelength of an object is equal to Planck's constant over that object's momentum. Now, the momentum could be the momentum of a photon, but particles have momentum too, right? Classically, momentum is equal to mass times velocity. So this equation is called the de Broglie wavelength, and is valid for both photons and for matter. Now, this was stunning in terms of what opened up in physics after this discovery. This discovery led to the whole branch of quantum mechanics being opened up as a part of physics. That at the smallest levels, electrons, protons, neutrons, and other similar particles behave both as waves and particles, like light does. Light travels as a wave, but interacts as a particle. Same thing is true for electrons, protons, and so on. This broke the Newtonian idea that electrons were little tiny bullets, that there were actual little tiny round particles in space. So all microscopic particles, it doesn't matter if they have mass or not, exhibit properties of both particles and waves. It's fundamental for all particles, this relationship between wavelength and momentum. You could calculate your wavelength, right? If you have a momentum, if you're moving, plug in your mass times your velocity into this equation, but you'd see that for very, very large momentum like you and I would have, large p leads to ridiculously small wavelengths. On the macroscopic world, we treat things like particles. We treat baseballs when we throw them as particles. Hockey pucks are particles, right? A ping pong ball is a particle. Cars behave as particles. They don't behave as waves. It's only when the momentum gets very, very, very small, because the particles get very, very, very small, right? The mass of an electron is very tiny, that the wavelength starts becoming appreciably large for us to study. This allows us to take small particles and look at the wave-like nature of those particles in unique ways. One unique way is the creation of what's called the electron microscope, sometimes the scanning electron microscope. The electron microscope, electrons actually have much, much, much smaller wavelengths than visible light does, which means that electrons can actually image particles or objects at a much finer resolution than is possible for visible light microscopes. And I'll post an image up here of a cool image from a scanning electron microscope. The detail you see in that photo is far greater than you could get from a normal visible light microscope. A visible light microscope just can't see this detail you would get out of a scanning electron microscope. So the whole point that a scanning electron microscopes work is a fundamental proof of the idea of the wave nature of particles. Now again, in the macroscopic world, this makes no sense, right? In the macroscopic world, baseballs and such don't behave as waves. And I cannot give you a real world analogy of what an electron does when it behaves as a wave or a particle. We just know that at the subatomic level, it has to. So this leads to some interesting consequences. First of all, the two-slit experiment we talked about, Young's two-slit experiment, when we talked about light and how light can be broken up into an interference pattern, that actually works for electrons as well. And there have actually been experiments which show electrons following the two-slit experiment. And we'll talk about more of that in the next video.